Today we're going to finish off Chapter 3, where we had already started talking about classical conditioning. Now, so far we've talked about the history of classical conditioning, some of the important terminologies and experimental setups that we might expect to see in this field, as well as some really cool research that allows us to apply, or at least study and visualize, classical conditioning from a perspective where the things that were learned were actually beneficial to the fitness of an organism. We wrapped up the end of last episode chatting about fear conditioning and other emotional conditioning as part of one of the four classical experimental paradigms that we tend to see with classical conditioning. And as promised, we're going to pick up right where we left off and talk about the other three of these classical paradigms. So we're going to move on to eye blink conditioning. And eye blink conditioning is actually fairly simple. And it's its simplicity that made it so popular initially and what has made it prevalent even to this day. So for eye blink conditioning, it's as simple as pairing a tone, an originally neutral stimulus that becomes a conditioned stimulus over time, and we pair that tone with a puff of air to the eye. And as you know, our eyes are very, very sensitive, so it's very easy to cause us to blink. Whether you move too quickly near someone's eyes, or, as in this case, we use a puff of air, the unconditioned stimulus of air coming towards your eye causes an unconditioned response of blinking. Now, this paradigm has been used for decades, but we're going to look at a somewhat more recent experiment, still 20 plus years old, but recent as compared to when they first started studying eye blink conditioning. But basically, we're going to look at eye blink conditioning in 5-month-old infants to see if they can learn to associate a tone with a puff of air to the eye. Now, this would be a great place to note that a puff of air to the eye doesn't have to be anything intense. It's definitely not painful. It's just enough to startle them and to create that blinking response. The setup for this experiment isn't very much different from other experiments we've talked about already. We have one group, which is going to be our treatment group, where our conditioned stimulus, our tone, is paired with a puff of air to the eyes. The way they did this is that the tone would play, and as the tone ended, there would be a puff of air. For our second group, our control group, this group was set up to be explicitly unpaired, which means that they still had the same number of conditioned stimuli, the same number of tones, and the same number of air puffs, our unconditioned stimuli, but they were arranged in such a way that they never actually overlapped. So instead of in our experimental group or our treatment group where they were always paired, in this second group, our control group, they never co-occur to try and keep them from forming an association between the two. Basically, they would occur randomly so that they didn't overlap. And so for this experiment, each infant would receive 2 separate training sessions, 1 week apart, and in each of these sessions, they'd receive multiple trials or multiple presentations. So let's take a look at the graph here. So we have on our y-axis the percentage of trials with a conditioned response. Basically, what percentage of trials did the child blink? And along the bottom here, we have our time variable again broken down into session 1 and session 2, each session having multiple trials. Now, the cool part here is that in our first session, the two groups don't seem to be any different. So our open squares are the paired group or our treatment group, and then the filled circles are our unpaired or our control group, and these two lines aren't statistically different from each other. So in the first session, there wasn't any evidence of learning here. But the cool part is that right away in the first trial, in the second session, so a week later when they came back, the very first trial, our paired group babies showed a much higher percentage of blinking when they heard the tone. So this tells us something interesting, that during this first session, even though the performance between the two groups didn't differ significantly, there was learning going on behind the scenes. But as we talked about earlier in the course, learning and performance don't always match. So here they were learning about this association between the conditioned stimulus and the unconditioned stimulus, but that learning wasn't evident until the second session. And that's where we see this significantly higher percentage of trials with blinking in the paired group than in the unpaired group. And that difference only got stronger here. So this group continued to blink more often after the presentation of a tone than did the control group, which is what we had expected. We just got some extra bonus information here too by learning that there was learning going on that didn't quite match the performance from that first session. The next paradigm that we want to talk about is called sign tracking, sometimes also called auto-shaping. So if you think back to our conversation about sequences of behavior, we had talked about squirrels trying to find food, and before they can consume a nut, they would have to approach an appropriate tree and climb that tree and search within that tree to find the right nut. So those sequences of behavior are pretty standard in nature. So animals need to approach food before they are able to consume it. Now there's a video here that I've linked on our eClass site, and then the link is down here as well, but it's to a video that shows a pigeon in an operant chamber, and it illustrates auto-shaping or sign tracking in a pretty cool way, because this process isn't necessarily something that we think would logically occur. But let's explain what it is first. So the idea is, in this operant box, there's, it's kind of hard to see here, but there should be some kind of button or a light, a place that would change some kind of stimulus prior to the delivery of food. So there's a light that turns on this wall in the chamber, probably up higher. I haven't watched the video in a little while, so I don't quite remember where it is, but that light turns on, and then shortly after the light is illuminated, then food would be delivered through the hopper here at the bottom. So when food is delivered, then the pigeon's able to eat. Now, the food and the light coming on, those are all automated entirely. The pigeon doesn't have to do anything to make either of those happen. But as the pigeons started to associate the light with the delivery of food, they started to treat the light as though it were food. Even though the light didn't cause the food to happen, they just co-occurred. And so because pigeons peck at their food, the pigeons would start to peck at the light because they associated the light with food. Now, sometimes in operant boxes, there are scenarios where animals have to push a button or peck at a screen in order to get food delivered. But in an auto-shaping task like this, the food would be delivered no matter what. It wasn't contingent upon the pecking, but the birds would still peck even if not pecking would get them the food anyways. Now, in trying to come up with an explanation for why this was happening, of course, scientists would try all sorts of combinations. They would try and light up the light without pairing it with food to see if the birds just peck at lights, and they don't. They only peck at lights that are associated with food. So this tells us that it isn't a reflexive behavior, but it does seem to happen whenever items are paired with a particular type of unconditioned stimulus. So if the unconditioned stimulus is food, as in this case, then they're going to do food-like behaviors whenever that conditioned stimulus is presented, whenever that light is presented. And I guess the even weirder part of this is that pigeons and a bunch of other creatures that have been tested on this will continue to do that behavior directed at that conditioned stimulus, even if it's inconvenient to be doing it. So if the food was dispensed here at the hopper and the light was on the complete opposite side of the box, the pigeons would still peck on the opposite side of the box instead of going over to the food hopper where they knew food would be delivered. Now in a box this small, that's not really a big deal, but if we scale it up and you start looking at much larger chambers, like this next example, where there's a difference of like 8 feet between where the unconditioned stimulus will be over here, which I'll explain in just a second, would be shown or released versus wherever the conditioned stimulus was shown. And they would still go to the conditioned stimulus, even though it had nothing to do with the arrival of the unconditioned stimulus. Now, this example is from our textbook. They were looking at quail, and quail tend to be studied for not so much food handling, but at least all the examples I've seen are of them doing sexual displays, because they will readily do sexual displays for females. And in this case, our setup was over here. At one end, we have sort of a trap door, and behind it is a female quail. So that is our unconditioned stimulus. So the male, whenever they would see a female, would then perform a sexual display around the female. But they started pairing a conditioned stimulus, which was just a wooden block that would be lowered into the chamber. They would lower that block in just before the female was released, and as the males came to associate this conditioned stimulus with our unconditioned stimulus of a female, they would approach and display at these conditioned stimuli. So they would go to the complete opposite end of the chamber and display for this block instead of going to where the female was being released. So again, it doesn't make logical sense that they would go in the complete opposite direction and do the behavior at this conditioned stimulus rather than doing it where they should logically be doing it for the unconditioned stimulus. And so they will do this, different species will do this with food. Here we have it with sexual displays. There's lots of different behaviors that kind of follow this same pattern. And there's another video of a pigeon in an operant box. This time it's a long box. So this would be a long box sign tracking experiment. So again, you can check out the video here, but effectively they have the hopper on one end of the operant box, and then they have their conditioned stimulus, which is a light, at the other side. And the pigeons would race over to the conditioned stimulus to peck at the light, even though it meant that they were very far away from where their food was being dispensed. And in fact, wasting time coming over here to peck at this circle and then have to run back to the food hopper meant that they had less time with their food, and it meant that they ate less. So this is even adaptively unhelpful. This would be negative fitness because you're losing out on something that's incredibly important for survival. So a very, very strange setup here. Now, within sign tracking and this whole idea, there are individual differences, which basically means that not every individual is going to display sign tracking. Sometimes we see what's called goal tracking. So here we can see another, basically the same kind of setup with a different set of stimuli. So our conditioned stimulus in this case is going to be a lever that gets presented or shown on the side of the cage here. And then our unconditioned stimulus is food again, and this time we're working with rats. So in the middle would be the hopper where the food is dispensed, and then on either side of the hopper would be places where a lever could be presented. And so during a trial, a lever would be pushed into the cage so that the rats could see and interact with it if they wanted. And then after 8 seconds, whether they touched the lever or not, the lever would be withdrawn and the rats would be provided with food. So within this experiment, about 1/3 of the rats ended up showing sign tracking. And so we're going to look at all of the stuff on the left side here first, so panel A and panel C. So we see here panel A is that they're paying attention to where the lever would be inserted, and panel C is showing the number of responses when we're measuring responses as interacting with that lever. And then across the bottom we have trials, which is just our measurement of time. So our black dot individuals were showing that a lot of them were learning, as they're learning that association between our conditioned and unconditioned stimulus, they're spending a lot of time interacting with the lever, and then as they learn that association, they're spending quite a bit of time pressing that lever, even though it doesn't cause the food to be delivered. And then because this is focused on number of lever presses, there's another about third of the rats that showed almost no interest in the lever. That's these white circles here. So if we want to know what these guys were doing instead, we're going to look at this goal tracking side. And so for goal tracking, this rat isn't focused on the lever, it's focused on the hopper. It's focused on where the food is coming, and the food is the goal. That's what they want. And so if we change our focus and look at number of responses, but this time to them putting their heads into the hopper or interacting with the hopper, we see that those white dots that hadn't been interacting with the lever were now interacting quite a bit with the hopper instead. So like we said, about a third of them chose to interact with the lever, our conditioned stimulus, and about a third of them chose to interact with the hopper, which is our unconditioned stimulus. This goal tracking makes a little bit more logical sense because that's where the food is coming from. So it makes sense to go where the food is. And then for the remaining third are these gray dots in the middle where they did a little bit of both. They weren't exclusively sign tracking or goal tracking. They kind of sat in the middle. So let's actually look at our definitions for sign tracking and goal tracking. So we said sign tracking, which is also called auto shaping. It's referring to movement towards a stimulus, our CS, that signals the availability of a positive reinforcer. So movement towards a lever, or movement towards the light for the pigeons, or whatever. For goal tracking, this is a conditioned behavior that's elicited by a conditioned stimulus that consists of approaching the location where the unconditioned stimulus is usually presented. So we're saying that this is a conditioned behavior where we know that the conditioned stimulus is associated with our unconditioned stimulus. So when we see that conditioned stimulus, we should go to the place where the unconditioned stimulus is usually presented. So the behavior that's been conditioned here is approaching that food hopper. Now, of course, seeing such a giant gap in behavior between those rats that were doing sign tracking and those rats that are doing goal tracking, of course, researchers would want to figure out what's going on, what's driving this. And so they looked into what other differences might exist between rats that preferred goal tracking and rats that preferred sign tracking. And in fact, there are a bunch of genetically based differences, one of which we care about quite a bit is actually closely related to drug addiction. So rats that are sign trackers end up showing a greater psychomotor sensitization to cocaine and some other drugs as well. They also see greater activation of the dopamine reward circuit in their brains and also elevated cortisone levels in their plasma. So all indicators that would make them much more susceptible to drug addiction. And so if we wanted to, say, apply this as a model to human behavior, then maybe this sign tracking might be an indicator of other things going on behind the scenes. Maybe we could look at this model system to look at things like impulsive behavior, say gambling, or drug abuse. So just another really cool potential application of some of the stuff that we're seeing here. Next, we're going to talk about conditioned taste aversion, sometimes shortened to CTA. And so our taste aversions and even our preferences are usually learned. There are some innate preferences for different foods. For example, young children tend to really like sweet things, even from a very young age. But a lot of our likes and dislikes from food come from learning and experience. But we're going to focus on the special case that is conditioned taste aversion. And this usually happens when we eat a novel food. It doesn't have to be novel food, but it usually works best if it's a food you've never had before or something that's a little bit weird or different. And as a result of eating that food, or maybe even just by chance it happens to occur shortly thereafter, you have some sort of aversive consequence. The way that this is set up is basically if you eat something new and that food makes you sick, then you form a conditioned taste aversion that makes you not want to ever eat that food again. From an evolutionary standpoint, that makes sense. If you eat something and it makes you sick, then you absolutely should not eat it again. The problem here comes in when sometimes you eat a novel food and you happen to get sick for a completely unrelated reason. And then you never want to eat that food again. And even weirder, even if you know or you are 100% sure that it wasn't the food that you ate that made you sick, maybe you know that it's because you had a stomach bug or because you got motion sick in a car, and you always get motion sick in a car. As soon as there's a pairing between some kind of new or different food and getting sick, our bodies are very, very inclined to form these conditioned taste aversions. So even if you know that it wasn't the food that made you sick, you're still going to be put off by that food. And this kind of taste aversion can actually occur with even a single pairing, so a single trial, which we've talked about trying to strengthen learning and form associations and stuff. Repeated exposure is usually key, but these conditioned taste aversions are so intense that they can happen just after one single occurrence. And it can even occur if the illness happens hours later. So we have this long delayed learning period, which again is very, very rare when we're looking at learning. Usually for a strong association to form, you need to have a very quick response where you would eat and immediately get sick for you to learn that they're associated. But for whatever reason, we've evolved this ability to connect getting sick to that food that you ate, even if it happens hours later. And this is probably evolved because a lot of poisonous foods wouldn't necessarily make you sick right away. It would have to wait until you had started digesting it or absorbing it into your bloodstream or whatever. But it's still beneficial to know not to eat that thing again in the future, so there must be some kind of evolutionary pressure there. At least that's the theory. And so here we have an example of conditioned taste aversion in a non-human animal species. So here we have a blue jay who decided that they were going to eat a monarch butterfly. But if you know anything about monarch butterflies, you know that they eat milkweed. And milkweed is specifically poisonous to most other creatures. So when this blue jay eats a monarch, it ends up getting sick later on, and as a result, they will never eat a monarch again in the future. So usually it only takes eating a single one of these butterflies to learn that they never want to do it again. And so while we've talked about the being evolutionarily advantageous for conditioned taste aversion to happen, and for it to happen after a single trial and to be so intense, there's also some evolution here on the monarch side to want to be recognizable so that the blue jays know when they see another monarch that that's the thing that made me sick. I won't eat that again. Now, one of the biggest examples that you'll hear talked about when we talk about taste aversions in humans is chemotherapy-induced nausea, because this is a big problem. Individuals who go to chemotherapy tend to get sick. Nausea is one of the major side effects of chemotherapy. However, it can cause problems because if individuals are going for chemotherapy and then they're getting sick, then their bodies start associating that sickness with the things that they'd eaten earlier in the day. And a lot of times when people are going through chemo, they want to comfort themselves. So they're going to eat their favorite foods. They're going to eat things that bring them joy. And then if they're getting sick afterwards and their body starts forming these taste aversions, then they no longer enjoy their food. They no longer like their favorite dishes, and they can start being put off by all foods in general. So there's some really cool research that's been done where they pair very odd ice cream flavors, stuff that you could never ever find in a grocery store, and they'll give that to chemotherapy patients before they go and get their chemo, so that when they get sick, they're a lot more likely to associate it with that odd flavored ice cream than they are to a meal that they've eaten multiple times in the past without any issue. And like I said at the beginning, when we started talking about these taste aversions, taste preferences can also be conditioned. And a lot of our taste preferences end up happening through something called evaluative conditioning. I always struggle with that one. And in evaluative conditioning, a neutral stimulus becomes more or less liked through association with something that is already liked or disliked. So I guess if you want to start drinking beer, and the first time you have beer, it tastes really gross because it has that very strong flavor and it's not something that you like right off the bat. But you start drinking beer when you go out with your friends. And so you start associating it with something that you like. So hanging out with friends is something you enjoy. And if you drink beer while hanging out with friends, then drinking beer will also become something you enjoy through evaluative conditioning. And this is how a lot of advertising works, where they pair something that you already like, say parties, with something that you maybe don't know anything about yet, a particular brand of alcohol. And they basically bank on this evaluative conditioning, making you associate their thing with something you already like so that you like it more. For practical applications of this conditioned taste aversions, beyond the example of chemotherapy, we can look at this really interesting study that was using conditioned taste aversion for conservation. So basically they have these blue-tongued lizards, and these guys tend to eat toads and frogs and other things like that. But they're in a particular environment where an invasive species called cane toads have moved into the area, and these cane toads are actually toxic. So if one of these blue-tongued lizards eats a cane toad, then they'll end up dying. And because it's an invasive species, they don't know not to eat them. So they're having a problem where these blue-tongued lizards are actually becoming very endangered because so many of them are dying from eating these invasive toad species. So these researchers decided to see if they can induce a conditioned taste aversion to get them to avoid eating these toads out in the wild. Now, for this bizarre experiment, they set up a situation where they would give these lizards conditioned taste aversions. So the first part of the experiment, what they tried to do was give these lizards, minced up cane toad meat, basically getting them used to the taste of it in very small amounts that wouldn't kill them. But they also injected the lizards after they ate the cane toad meat with lithium chloride. And lithium chloride is just a chemical that makes them sick. On our y-axis here, we have the amount of food consumed in subsequent trials. And across the bottom here, this would just be number of weeks after training. So this is our time variable here. And so our open circles are going to be our control group. So these are the toads that were injected with just saline. And then our closed circles here are our treatment toads. These are the ones that were injected with the lithium chloride, which would make them sick. And now, while we do see a drop-off in the amount of toad meat that was eaten by the experimental group, it didn't stay down for long. In fact, by the 7th week, even by the 6th week here, we're seeing a heavy overlap in these error bars, which is telling us that the two groups aren't significantly different in the amount that they were eating. So basically, it worked for a short amount of time, and then they went back to eating a normal amount of cane toad meat. So it wasn't really viable. And also, in a practical side of things, it's really not feasible for researchers to inject all lizards, to try and induce this kind of a result, to try and give them all a conditioned taste aversion. That's where study 2 came in. So same exact setup here, except this time, instead of injecting lithium chloride, they had it mixed in with toad meat that was prepared as sort of toad sausages, is how they're describing it. And so the control group here ingested just toad meat sausages, and our experimental group, again, the solid dots, they were given sausages of toad meat mixed with lithium chloride so that they would get sick. And so here, there's a much greater drop-off in how much toad sausages they would eat after the fact, and that number stayed lower. Now, that's all well and good, that's all in a laboratory, but would this actually get them to avoid real-life toads? Would this translate into nature? So let's look at this graph here. This time our y-axis, is latency to approach a container that had a live toad in it. So basically, the higher this number, the longer it took them to approach that toad. And then this would be when there was an empty container the first week, a live toad right after that. So this would kind of be like our baseline. Then a live toad immediately after, then 2 weeks later, they had a live toad again, and then 10 weeks beyond, they did it again. And so right off the bat, there wasn't really much difference between the groups, but as we get into the 10-week period, we do see that the treatment frogs, the ones that got actually lithium chloride dosages, then they did end up showing a longer time to approach the toad. This was only in our injection groups, which didn't show great promising results in the lab, but they seem to work in something that's still in the lab, but a little closer to what they would have encountered in nature. But weirdly enough, they didn't find a statistical difference between the groups for the toad sausage groups for the second experiment. So we kind of got mixed results here, where there's a lot of effort put into this. Either you inject individual toads and get sort of a difference, or you give them the toad sausages and it doesn't seem to work in the real world application. So we're kind of left at, there's potential that there could be some field applications to this, but where it's sitting right now, not so much. But it's an interesting experiment, and it was a good idea, and in the future, it's kind of interesting to follow this and see if they come up with any other solutions or any better methods to make this actually work, because from the conservation perspective, this would be a really important thing for them to be able to do. All right, that's enough about toads and lizards. Let's get back to the lecture proper. So we're going to talk about two types of classical conditioning. And technically, we've already really talked about our first of these, which is excitatory conditioning. Pretty much all the examples that we've mentioned so far have all fallen under the category of excitatory conditioning. And this is when you learn of a relationship between the presence of a conditioned stimulus and the subsequent presentation of an unconditioned stimulus that's associated. We will be talking shortly about inhibitory conditioning, and this is where you learn to predict the absence of an unconditioned stimulus. Basically, where our conditioned stimulus tells us when the unconditioned stimulus will not be happening. But this doesn't necessarily have to do with punishment or aversive stimuli, though it does tend to co-occur quite a bit. But we'll come back to inhibitory conditioning a little bit later because it needs its own conversation. But let's talk more in depth about excitatory conditioning procedures first. And this should be quite a bit of review, stuff you would have covered in previous classes, so we won't spend too much time here. So like I said, excitatory conditioning is focusing on a conditioned stimulus paired with an unconditioned stimulus. Basically, our conditioned stimulus is going to occur, and then the unconditioned stimulus occurs at some point, either after, during. We're going to talk about that. But it's kind of like our tone plays and then dogs get food. And so with this setup, organisms are learning some kind of association between our conditioned stimulus and unconditioned stimulus. So following repeated pairings, the presentation of that conditioned stimulus alone leads to behavior that was previously associated only with the unconditioned stimulus. Because we've learned to associate the conditioned stimulus with the unconditioned stimulus, we'll react to our conditioned stimulus pretty much in the same way we would react to the unconditioned stimulus. And like I said, all of our examples so far have been talking about excitatory conditioning procedures. So let's get into some of the terminology and ways to talk about some of this stuff. So here, we're setting up the idea of a conditioning trial. So this whole unit here would be a trial. And one of the major factors in this course of classical conditioning is the relative timing of the conditioned stimulus and the unconditioned stimulus. When are they presented relative to one another? So the way that we're going to read these diagrams is that as we go from left to right, we're basically looking at time progressing. And then we have two graphs that are showing one with the conditioned stimulus, one with the unconditioned stimulus. And basically we're looking at conditioned stimulus is off, 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 off. And then when it jumps up, the conditioned stimulus is on. It stays on for this amount of time. And then it turns off when it goes back down again. And then it continues off. And we can read our unconditioned stimulus the same way, where we would come across here, where it jumps up, that's where it turns on, and then it stays on for a time, and then it drops back down again and is off again. And so we can read this as our conditioned stimulus turns on, stays on for an amount of time, and then as it turns off, our unconditioned stimulus turns on. And then the unconditioned stimulus stays on for about the same amount of time, and then it turns off as well. So that's how we're reading these diagrams. And so like I said, this whole thing is considered a single trial because it's one presentation of our conditioned stimulus and our unconditioned stimulus. So we can call it a conditioning trial or just a trial. And normally we're going to repeat these multiple times to form that association between the conditioned and unconditioned stimulus. So here we have two trials, and the space or the gap in between our trials, the amount of time from the end of one trial to the start of the next trial, is called our intertrial interval. So that's that gap in between our two distinctive trials. We can also talk about our interstimulus interval, or ISI, instead of ITI. And this is because we're looking at the difference from the on time of our conditioned stimulus to the on time for our unconditioned stimulus. So how much time elapses between the start of our conditioned stimulus and the start of our unconditioned stimulus. You might also see this called a CSUS interval because it's the interval of time between the CS and the US starting. So here we have 5 common procedures where you will see for pairing our CS and our US. So short delay conditioning, trace conditioning, long delay conditioning, simultaneous conditioning, and then a weird one which is backward conditioning. And so these are the exact same setup here, just one of them is shaded now, so it looks a little bit different. But let's break each of these down. So short delay conditioning, we have our conditioned stimulus presented alone, but our unconditioned stimulus starts before the conditioned stimulus ends. So if this was a tone being played and then a dog getting food, the tone would still be playing when the dog gets food, and the tone would stop playing before the food was taken away. This overlap here is kind of the signature of our short delay conditioning. This is usually the most effective of the conditioning procedures, having a very short delay here. For trace conditioning, it looks really similar, except that our conditioned stimulus is going to stop just before our unconditioned stimulus starts. So they don't overlap, and our conditioned stimulus happens first, then the unconditioned stimulus. And the longer the gap between these two, the less conditioning you're going to see, or the slower the learning is going to be. So in these cases, a longer ISI is going to be a bad thing. Now, because of this setup, instead of having animals focus on the start of our CS and the start of our US, what ends up being important is actually the end of the conditioned stimulus. And that's why the longer the delay between the end of this trial and the start of the next one, we're going to see less and less learning. So they care more about the end of the conditioned stimulus for this particular type. Our long delay conditioning basically looks like a dragged out version of our short delay conditioning. So our conditioned stimulus starts, but instead of it only being short, say the same length as our unconditioned stimulus, it's going to drag out. So our CS is on for a much longer time. There's still this overlap here where our conditioned stimulus is still on when the unconditioned stimulus is presented. But the problem here is that our conditioned stimulus is no longer precisely telling us when our unconditioned stimulus is going to happen. Because this long delay here, we don't quite know when after that onset time this is going to happen. And the longer the conditioned stimulus is on, the less sure we are of when the unconditioned stimulus is going to happen. So the longer this gap here, the worse learning we're going to see. We can also see simultaneous conditioning. This is one of the easiest ones to figure out, where CS and US both start at the exact same time. This one isn't fantastic for learning because you kind of get distracted from the conditioned stimulus by the unconditioned stimulus being presented at the same time. So you pay more attention to this because it's relevant, and this is ignored because it isn't immediately relevant. And then our weird one, which is backward conditioning, where, unlike all of the others, our unconditioned stimulus happens first. So our unconditioned stimulus occurs, and then the conditioned stimulus happens. Results for using backward conditioning are very inconsistent. So, for obvious reasons, it's kind of hard to think back to things that had happened previously. In nature, it can be adaptive to know about things that happened in the past. Say you got attacked by a wild animal. If you were attacked and you didn't see it coming, then you wouldn't have gotten to see the attacking animal until after the scary event had happened. So if you survived that attack and saw the predator leave, then you would get that information of their visual appearance as the conditioned stimulus after the attack. And it makes sense to remember what it looks like to avoid it in the future. So it is a good way to be able to associate those, but it doesn't always work that way. It is a lot harder for animals to form an association with something that happened in the past. Now, I've already kind of said this verbally, but here is a graph showing just how important that interstimulus interval is. So here we have the conditioned responding, which is basically how much learning is happening, and then how long of a delay between our CS and our US. That's that CS-US interval. And so when it's short, we see a quick rise. There's sort of an optimal point right about here, and that amount, whatever that interval is going to be, will change depending on what kind of stimuli we're looking at. But the pattern holds pretty consistently. But so we peak fairly early on when we have a nice short interval, and then as that interval gets longer, we see less and less and less learning. So our short delay conditioning is a lot better. Over here would probably be something like simultaneous, where they were presented at the exact same time. So there's 0 for that CS-US interval, that would be this point here. So we want a short delay, and the longer that delay gets, the less learning we see. So I've already dropped some hints about what makes for strong associations, but we're going to go over them again real quickly here. We are going to talk about contiguity and contingency. Contiguity is basically that the events occur close together in time and space. If your CS and US happen on completely opposite sides of a room, you might not find it easy to associate them. Or if they take place very long times apart, again, you find it very difficult to learn about that association. For contingency is basically, does the CS come before the US? Does the US always follow the CS? Is one event going to be preceding the other? Like, are they always related? That's contingency. So contingency is how strongly are they associated? How much do we trust that one comes first and the next one comes after? How closely are they related? And for other things like repeated trials, more intense stimuli, that sort of thing that we've already talked about previously, those also all apply here as well. Okay, so how do we actually know that learning has occurred? I think I might have mentioned it in the past, but we're almost always going to see training followed by testing. And the testing usually occurs in extinction. Basically, you're going to present the conditioned stimulus alone, where it isn't followed by the unconditioned stimulus. Because we want to see, how does the animal behave to just the conditioned stimulus? So what is our conditioned response? And it's really hard to get a clear picture of that if we're still presenting that unconditioned stimulus as well. And so when we do these test trials, we can look at the magnitude of the CR. How much of the responding are they doing? We could look at probability of that CR occurring. So if we do multiple test trials, how many trials do we see that behavior? So 50%, 100%, what's our probability? Or we might see latency until that conditioned response occurs. How long does it take for the lizard to approach a toad? All of these are possible, and we've seen examples of all of these up to this point. We could also compare between two groups. Another thing that we've seen, we can have one group that experiences the learning condition and one group that experiences the control condition. And then we can compare differences in their magnitude, probability, or latency, or whatever other measure you can come up with. If we want conclusive evidence of learning, then we're going to need to compare two groups, and we're going to want to have some kind of reliable measure of how that behavior is different between the two groups. And of course, if we're conducting good science, we're going to want some kind of control here. We have to watch out for what's called pseudo-conditioning. Basically, we're worried that exposure to just the unconditioned stimulus could lead to responses similar to the conditioned response. So maybe dogs just salivate all the time, and in fact it had nothing to do with the tone, they were just salivating spontaneously. So how do you control for this? We can use random control, where you would present your conditioned stimulus and the unconditioned stimulus at random. This would be in our control group. So they'd get 10 tones and 10 bowls of food presented at random points in time. With this random, there is a chance that we'll see overlap between the conditioned stimulus and unconditioned stimulus just by pure chance. Or we could do what we've seen fairly recently, which is explicitly unpaired controls, where the conditioned stimulus and unconditioned stimulus are presented with an intentional gap of time between them. So they never occur at the same time. There's always some kind of buffer where they cannot co-occur. This, for obvious reasons, is the most effective type of control, because then we know that there isn't any possibility of them learning an association between the CS and US, because the CS and US have absolutely never been presented together. an interesting little aside here before we get into inhibitory conditioning. We're going to talk very briefly about the temporal coding hypothesis. And this basically tells us that Pavlovian conditioning procedures lead not only to us learning that there is an association between the US and the CS, but we also learn when our US occurs in relation to the CS. So the setup here is that they have a novel kind of setup where the conditioned stimulus happens, and then 150 milliseconds after that conditioned stimulus, the US would be presented for the first time, and then at 100 milliseconds after the CS had been presented, the US would be presented a second time. And they were looking to see if, in this case, rabbits could show this sort of precise control of responding to those two time frames. So instead of learning just between one CS and one US, can they form a link between the CS and two USs at distinct time periods? And so here we can look at day one. They wouldn't necessarily know to respond to anything because they're just starting to learn it. But as time goes on, day 4, day 6, day 8, day 10, we see more and more responding. So this is our CR magnitude. So how much responding are we getting? And then when is it happening? So we do see a nice peak forming at just before that 200 millisecond mark. So it's not perfect for our 150 millisecond onset, but it's close enough. And then we see another one over here, just past that 500 millisecond mark. And that one takes longer to show up and isn't as intense as the original, which might just be due to the fact that animals tend not to be good at tracking time. So they'd be a lot better at tracking something closer in time. So this is the presentation of the unconditioned stimulus that happens closer to our conditioned stimulus. So it would be a lot easier to resolve that time appropriately, whereas the second one, which happens much later, would be a little bit harder to pinpoint, but we do still see an increase in responding, which is really, really cool. So we don't just learn that there is an association between the two, we can also learn when it occurs with this nice increase in responding here. All right, so moving on to inhibitory conditioning as promised. So this is just a reminder. We did excitatory conditioning, and now we're moving on to inhibitory conditioning, where we're learning to predict the absence of an unconditioned stimulus. So our CS is telling us when the US will not be happening. It happens to be beneficial to be able to predict the presence or absence of an unconditioned stimulus. Specifically, if we're looking at aversive events, predictable aversive events are much better than unpredictable aversive events. There is tons of research that shows that the stress and the sort of wearing down on the body that happens when organisms are put into unpredictable aversive environments is much, much worse than if they're in aversive environments, but those environments follow predictable schedules. And learning to predict this interaction, learning to predict when that US will not be present, allows you to predict when bad things will not happen. So it gives you windows in which you can relax. So for example, if a child is being bullied every time the teacher leaves the room, then the teacher is going to act as a conditioned inhibitor for us. So when the teacher is present, they indicate that nothing bad will happen in their presence. And then the child knows that if the teacher leaves, that's when the bad thing can happen. Now, in order to have inhibitory conditioning, have a moment there, we have a prerequisite. So for the removal or absence of an unconditioned stimulus to be meaningful, that unconditioned stimulus must occur sometimes. Basically, we need our unconditioned stimulus to have some kind of excitatory context. Basically, Our sign here that says, sorry, we're closed, is only a meaningful signal if it's on the door of a restaurant that is sometimes open. If it's on the door of a restaurant that's been decommissioned and abandoned, then that sign isn't telling us anything, and it doesn't serve as a conditioned inhibitor because there isn't a time when this restaurant is actually open. So this serves as a conditioned inhibitor. It signals the absence of our usual unconditioned stimulus of the restaurant being open because the restaurant is usually open. So that's the excitatory context, is that the restaurant is usually open unless this sign is up. So we can talk about two distinct types of conditioned inhibition procedures. The first is the standard conditioned inhibition procedure, or the Pavlovian procedure. That's a mouthful. And the second is our negative CSUS contingency. So let's look at our standard conditioned inhibition procedure, or our Pavlovian procedure. And so in this case, we're going to have a conditioned stimulus with a plus, indicating that it's an excitatory context. So our CS plus is creating this excitatory context. We're then going to have a CS minus, which will end up becoming an inhibitor later on. And then we have our unconditioned stimulus. And so we have two different types of trials, trial type A and trial type B. In trial type A, we get the CS plus, and shortly after that CS plus happens, our US also happens. So this is telling us that when the CS plus happens, the unconditioned stimulus is also going to happen. So when we see the CS plus, we learn to expect the US. Trial type B modulates that. And this time, when the CS plus happens, and it's paired with a CS minus, so we're seeing a simultaneous delivery here, we don't get any US at all. So basically, the presentation of both CS plus and CS minus gives us no unconditioned stimulus. That's our trial type B. And so when we're doing training, we would intermix these two, where they get some A's and some B's, so that they should learn that when you get the CS plus alone, you're going to get the US, and if you get the CS plus with the CS minus, then you get no US. And this differential presentation allows us to give that CS minus inhibitory properties. Basically, we learn that it's a protective factor. When it is present, the excitatory nature of the CS plus is effectively neutralized. Now, that's really confusing. So let's do it with an example. So we're going to look at, you're sitting at a traffic light. The light is red. If you are sitting at that red light and you decide to go anyways, you have a high chance of getting hit by another vehicle. So when that light is red, this bad thing, like getting hit in the intersection, could happen. So that's our trial type A. Trial type B is that there's a police officer present, and they decide to wave you into the intersection. So even though the light is red, the officer is telling you that it is okay. And if you go into the intersection, you're very unlikely to get hit by other vehicles because the police officer is there directing traffic. So our police officer is our CS minus. They're basically a safety signal that tells us that even though our CS plus is here, nothing bad is going to happen. Next, we can look at the setup for a negative CSUS contingency, and this one's a little bit easier to grasp, I think, anyways. So here we just have a CS and a US. There's no need for a CS plus. So here our CS is effectively just a CS minus. So we don't have that CS plus. And what we can see is that the US is going to happen periodically, and the CS happens periodically, but they never happen together. So this tells us that if our CS minus is happening, we know that we will not experience an unconditioned stimulus. So this US is occurring, but it never occurs right after our CS minus. So this tells us that when that CS minus is happening, we are safe. So our CS minus tells us or signals a reduction in the probability that the US will occur. Now this works best if there's a 0% chance of getting the US while the CS is present. Basically saying that there's never any overlap between them. We see a lot more learning when there's no overlap at all. But we still see some learning even if it's just a reduced probability of them co-occurring. All right, and just like with our excitatory conditioning where we asked, how do we measure that conditioning? We can ask again, how do you measure inhibitory conditioning? So for the excitatory conditioning, we were measuring a new conditioned response that was being elicited by that conditioned stimulus. And we were comparing that to how much responding would have been done if there wasn't a conditioned response, basically comparing between our two groups. For inhibitory conditioning, we have three distinct measures that we can talk about. We have bidirectional response systems, compound stimulus or summation tests, and retardation of acquisition tests. And we're going to talk about each of these very, very, very quickly. For some measures, they can work in a bidirectional fashion, basically meaning that your measured response can either increase or decrease. It can move in one direction or the other, hence bidirectional response here. So we can measure the increase, our conditioned excitation, or decrease, conditioned inhibition, from some known baseline. So we can measure the distance toward or away from something. So if you start 10 meters away from something and you move towards it or away from it, we're getting a bidirectional measure. We can also look at eating or drinking more or less of something. There's lots of stuff that fits this bidirectional measure. It doesn't work for all behaviors. Things like freezing behaviors don't really work because when you freeze, there's no measure at all. So it's hard to get less movement when you've already frozen. Same with eye blink. There's sort of a set rate of how much blinking people will do in a set amount of time. So you can only see slight fluctuations. You can see more, but not necessarily less, because we always are going to blink at least enough to keep our eyes moisturized. But I'm sure you can imagine a graph showing a line going either up or down, indicating that we're seeing more or less movement, moving towards or away from something, or eating or drinking more or less. Pretty straightforward. Next, we have a compound stimulus test, or sometimes called a summation test. This one's a little bit more complicated, so we're going to talk through it with an example. Now, this test is based on the idea that conditioned inhibition is going to inhibit or counteract our conditioned excitation. Basically, the presence of our CS minus should affect responding in some way. So if we have conditioned excitation, then we should see a reduction in responding because of the CS minus. So long story short, we're going to be measuring how the presentation of this CS minus suppresses responding that is usually elicited by that CS plus. Like I said, it's a little bit complicated, so we're going to go through an example with images, because that's what helps me for this. So in this scenario, we have training set up where we have thirsty rats, basically meaning that rats had been deprived of water so that when they were given the chance to drink from a water bottle, they would readily drink from that water bottle. That would be our establishing operation, as it were. And our measure here of behavior is looking at how long it takes for them to drink continuously for 5 seconds. And so here the idea is that if a rat is say anxious or nervous about something, they would drink very briefly and then stop, and then drink briefly and stop, and drink briefly and stop. So if they are more nervous, it would take longer for them to sit still and drink for a full 5 seconds than if they were calm. So a calm rat would take very little time to drink for 5 seconds because they would just sit there and drink, whereas an agitated rat would take much longer to do that. Now, we're going to have a bunch of different stimuli here. Our first stimulus is A+, which is a visual stimulus, and because it's plus, it's an excitation stimulus. And in this case, it's just a flashing light. And so this flashing light is always paired with a shock. So whenever that light is flashing, whenever it stops flashing, there's a shock. X would be an auditory stimulus, so a tone that would play in the background. When we had the flashing light and it was paired with X, there was no shock. So AX is labeled with a minus because there is no unconditioned stimulus. So our shock here is our unconditioned stimulus. We then introduce a new auditory stimulus, which is B+. B+ would be a different sound presented in a different chamber so that they would be learning it somewhere else. And that has a plus on it, so it is always paired with a shock. So we have two stimuli that on their own would be paired with shock. B+ and A+ are always followed by shock. We teach them that A with X is a minus, where there is no shock. So our X should be giving us some conditioned inhibition. We're going to come back to Y in just a minute. But what we've set up so far with what we've talked about here is that we have conditioned excitation to A and B, where A on its own is paired with shock and B on its own is paired with shock. And we have a conditioned inhibition to X, where X being presented with A means that it's safe and there will be no shock. So now we want to ask, what did these rats learn about X? So if we hop to the graph on this page here, we're looking at mean time, which is a log measure. Basically, it means that the longer this bar is, there is lots and lots more time in there. And again, we're measuring how long it took the rats to drink for 5 seconds straight. So it's a very, very long time at this point here. And so if we look at what we had already established, we have our B and our A, which on their own are sort of B+ and A+. So it would take them a very long time to learn to drink for 5 seconds straight because they're paired with shock, so they would be anxious. We also have AX, which we had talked about was learned to be a conditioned inhibitor. So here, when A and X are paired, it takes them a little bit of time, but a lot less time than A or B on their own. So it's acting as a conditioned inhibitor because AX has much less responding than A on its own, or much less time taken to drink for the set amount of time. I guess we're looking at latency here. Then we would look at novel pairings. So now we look at BX. So they've learned that B was conditioned or has conditioned excitation, and X acts as a conditioned inhibitor. So B plus X, they ended up treating it as, again, a conditioned inhibitor here as well, where we see much less time taking to drink for 5 seconds. So there's a much less amount of time here. So yeah, X act as a conditioned inhibitor in a novel scenario. Because from our setup here, we never put B and X together. So the only way they could have learned about X was from its association with A. And so they treated X with B the same way they treated X with A, so they've generalized and called it a conditioned inhibitor. Now this is where Y comes in, and Y was set up as a novel stimulus, another tone. There was no pre-training at all for it, and it was basically there to serve as a control, because they wanted to show that compound stimuli wouldn't just automatically cause less responding. So they were saying that if any stimulus paired with A or B could cause a decrease in responding, then introducing this new stimulus Y would lead to BY being low, just like BX was. But instead, we actually see quite a bit of responding here. So BY was treated just as bad, if not worse, than B on its own. So they didn't know anything about Y, and there wasn't a natural assumption that Y should be a conditioned inhibitor. So it's just sort of a control here, showing there wasn't something else going on here. So we've kind of already said this, but B and X were never presented together during training, but we still saw that drop in the amount of time it took to drink for 5 seconds. So X became a general safety cue. They generalized to other scenarios where they treated BX the same way they treated AX. Now, our next and last type of test is actually going to build off of the same setup that we just did. And so this type of test is called the retardation of acquisition test. And so here, retardation just means a slowing or a disruption of. So we're looking at a slowing or disruption of the process of acquisition. So the idea here is that if a stimulus actively inhibits a particular response, like X did for the previous experiment, then it should be especially difficult to turn that stimulus into a conditioned excitatory CS. So in order to flip it from a conditioned inhibitor to a conditioned excitator, I guess we'll stick with conditioned excitatory CS. Basically, to get it to serve the opposite purpose, it should take a lot of effort because we've already learned that it inhibits, so it should be really hard to make it do the opposite. Another way to say it is that the rate of excitatory conditioning should be slowed if that conditioned stimulus was previously established as a conditioned inhibitor. So again, just like X in our previous example. So we're going to look at X, which had been previously conditioned as a CS minus, a conditioned inhibitor, and Y, which had no previous training at all. So exact same setup as before, but we're just looking at X and Y now. And so for our training, both X and Y would be followed or paired with a shock. And then for testing, they would see how long it took for them to drink for 5 seconds. So the same exact test as before. And we see a nice clear result here, where Y, which had no prior learning, it took them a very, very long time to drink water for 5 seconds straight. So they definitely had that conditioned excitation here. But X was very, very low still. So we can say that because it had already been established as a conditioned inhibitor, it was really hard to turn it into something excitatory. So we see this dramatic difference here because of what had already been learned about X from the previous training. Now, you might have figured this out already, but because this test and the previous test are both looking at the same stimuli, the same kind of setup, just from different angles, they did that for a reason. And that's basically that when you conduct only one of these tests, if you only conducted a retardation of acquisition test, or if you only conducted a compound stimulus test, then you couldn't be certain that what you were seeing wasn't due to some other external factor. But because we've come at it from two different sides, we're going to be a little bit more confident in our conclusion that X is a conditioned inhibitor, and that we have some idea of the mechanism going on based on multiple tests that are showing us very similar results. So it's always a good idea that if you can, to try and use a couple of different tests to see that all of those different results lead you to the same conclusion. All right, and so for our very last slide here, we have the take-home message that classical conditioning is everywhere. And it's a lot more than what people tend to think of when they think of classical conditioning. It's not just something that occurs in the lab. We've talked about fears and phobias. So classical conditioning is involved in the development of them, and maybe understanding that development can help us get rid of them, or at least alleviate them a little bit. We have our food preferences and aversions, which can play a major role in our lives, and we have all of the functional research that we've talked about, where we can see classical conditioning actually impacting things like fitness. So big take home is classical conditioning is more than people think, and it's very cool despite the way that it's presented, at least in first year psychology and that sort of level. But a very neat topic, and we'll talk more about it in the next chapter as we delve into some of the mechanisms that are driving all of these connections that we're seeing.